Hello, my name is Hana Huwaida binti Nusra Effendi with an metric ID MA18161. So the title for our experiment 2 is Flow over Immersed Body and Boundary Layer. Chapter 1 Introduction. So flow over immersed body, we can see that when a solid body is entirely immersed in a moving fluid, it will be subjected to some pressure or force. So according to the Newton's law of resistance, the force exerted by a moving fluid on an immersed body is directly proportional to the rate of change of momentum due to the presence of the body. Next is a boundary layer is a thin layer of a moving gas or liquid in contact with the surface, such as the inside of a pipe or the wing of an aeroplane. So shearing forces act on the fluid in the boundary layer. If the fluid is in contact with the surface, a range of velocities exists throughout the boundary layer, extending from maximum to zero. Next, this is the objective for our experiment 2 is to develop a full fluid flow measurement system and evaluate the drag and lift forces acting on a symmetrical aerofoil at various angles of attack. Next is to estimate the flat plate velocity distribution. And lastly, to calculate the thickness of the boundary layer of a flat plate subjected to longitudinal flow for both rough and smooth surfaces. Chapter 2 Theory. Despite the fact that the angle fluid equation had been known for a long time, their solutions were unable to accurately reflect observed flow effects such for installing. So Prime was the first to realize that when we proceed from a layer near the surface to a layer further away, the amplitude of inertial and viscous forces change. When a particle just above the surface collides with particle adhering to the surface, the particle just above the surface slow down and cause a thin layer of fluid to form at the surface, with a velocity that varies from zero at the surface to the free stream value further away. Next is aerodynamic forces between the fluid and the object are generated in this boundary layer. The drag and the lift forces are the two most important aerodynamic forces. So the diagram below shows the boundary layer. So when a fluid passes through an object, it comes into contact with the resistant forces that inhibit it from moving in the original direction. So this diagram below shows the drag and lift forces that occur. Next is because the dividing streamline and the stagnation point go down, more airflow above the wing and the velocity below the aerofoil decreases. As a result, the pressure beneath the aerofoil is greater than the pressure above it. So this is the equation used for drag force and lift force. In the same way that flow in a duct can be laminar or turbulent, so can flow in the boundary layer. So pressure gradient, surface roughness, heat transfer, body forces, and free stream disturbance are all elements that influence boundary layer transition. So this figure shows flat plate boundary layer. And lastly, this implicit flow assumption cannot be used when shear forces are significant near a solid surface. As a result of the fixed solid surface, fluid movement is slow, generating a confined, slow-moving boundary layer. So this is the equation for the implicit flow assumption. That's all from me. Thank you.
Assalamualaikum warahmatullahi taala wabarakatuh. My name is Wan Ahmad Abqari, BMM Rusdi. My matrix ID is MA18168. Today I would like to explain about the methodology for this experiment. For the first experiment is the flow pattern of the symmetric aerofoil at different angle of attacks. And this is figure 1 show the experiment setup. We have a flow bench, smoke controller, manometer, aerofoil model, and radial fan speed controller. And, and it has a 0 angle of attack and 30 angle, 30 degree, and 45-degree angle of attacks. This is the process of the experiment. At first, the experiment is set up as follows, as they shown in figure 1, and Next, attach the aerofoil model to the airflow bench using screw. The next start of the experiment, the attack angle was set at 0 degrees, and turning on the switch caused the radial fan to spin. The radial fan speed control starting speed is set at 12. The data is tallied and recorded, and the smoke control is then pressed to release smoke into the flow to see the flow of the air on the aerofoil. And next, a photograph of the flow of the aerofoil is taken and increase the speed of radial fan by 1 till it reach 90. And the last one is repeat step 5 to 8 for 30-degree and 45-degree of attacks. And for the precaution step is test all of the gear and equipment before commencing the experiment to confirm that they are in good functioning condition. And next, the angle of attack must be measured precise to guarantee that the reading is accurate. And the last one is the smoke is in the smoke controller should be visible to the airflow. And for the experiment 2 is a flow over flat plate. This figure to show the experimental setup for the experiment 2. We have a manometer, uh, receiver, and the pitted tube. And for the next picture is the plate, which is we have two plate, rough plate and smooth plate. And this is on the process of the experiment 2. The experiment is set up in the method as shown. The flat plate with a smooth surface is put into the airflow bench. The first distance is set to 0 and the following distance is measured. The vernier caliper are connected to the pitted tube. The pitted tube is first touched to the surface of the plate as the first data. The radial fan is then turned on and any data are recorded and tabulated. The plate distance is raised from 0 mm to 150 mm by 20 mm, while the pitted tube distance from the flat plate surface is increased from 4 mm to 32 mm by 4 mm. And the last one is the experiment is repeat from step 5 to 7 for the rough surface. For the precaution step for the experiment 2 is in order for the data to be accurate, the plate changing distance must be consistent. Tighten the plate completely. Make sure the pitted is touching the plate surface. The operation of the vernier caliper is checked. That's all for me. Thank you.
Assalamualaikum and good day. My name is Muhammad Irakan bin Madjari from Group D Section M01. Today I'm going to talk about the result that I have done for this experiment. So, this experiment we have done two experiments. For experiment 1, we have done the flow pattern of symmetric aerofoil at different angle of attack. For my result, here I have compiled all the three results for the different angle of attack. For the 0 degree, 30 degree and 45 degree. Then moving on, here is the question that involves with the calculation for all the relevant result for the drag force. For the lifting force, here you can see that the initial height is 237 mm. The area platform area of aerofoil is 0.0016 meter square, and then the frontal area for the different angle of attack. For the 0 angle is equal to 0. For the 30-degree angle is equal to 0.00315 meter square, and the 45 degree angle of attack is equal to 0.04454 meter square. Then here is the calculation of the drag and lift force for all the three different angle of attack, for 0 degree, for 30 degree, and for 45 degree. Then here we can see that the graph of drag force versus fan speed. As the fan speed increase, the drag force will decrease. Except for the zero angle of attack where there's no contact area, so no visible drag force. Then moving on, here we have the lift force versus fan speed. As the fan speed increase, the lift force will decrease. Then moving on, we have the experimental flow over flat plate. In this experiment, here is the result for the smooth surface flat plate. Then here is the result for the rough surface flat plate. For the smooth surface flat plate, we have measured the velocity and the knot number. Here we can see that the overall result for the smooth surface. We have the graph for boundary layer versus head, boundary layer versus velocity, and boundary layer versus knot number. All three of them show the same pattern, which is decreasing over time as the head increase, as the boundary layer increase. Then rough surface. Here is the result for the rough surface, for the velocity and for the knot number. Just like previously mentioned before, all of them show the same pattern, which is as the boundary layer increase, the mentioned result will decrease. Then here we have the velocity versus distance of plate for smooth surface. You can see that the plate distance increase, the velocity will increase over time, then it will decrease at the 17 millimeter. Then velocity versus distance of plate for rough surface. In this graph, we can see that at 40 the velocity will decrease, then it will increase back to 80. So that's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Razia, metric number MA18092. I will be covering the discussion part for both experiment, that is flow over immersed body experiment and boundary layer experiment. I will be mainly answering questions from both lab sheet. So let's start with flow over immersed body experiment. So the first question is, which body creates the most smooth streamline? The smoothest streamline is generated when the angle of attack is zero, that is, by attacking at zero angle. This is the case because the boundary layer on the top and bottom surface only exhibit minor pressure gradients at small angles. They are attached for almost the full chord length and are at the attack point. As you can see here in the figure, the streamline is very smooth since the angle of attack of the airflow is at zero angle with the body. Next question. What does smooth streamline portray? When a moving body compels to the air around it to flow in precise pattern, a streamline is generated. Laminar flow refers to the smooth, consistent airflow patterns that surround an item. They illustrate that moving an object through a fluid causes the least amount of disruption. Next question. What happens when the wing profile at 30-degree angle compared to the normal? When the wing profile is at 30-degree angle, the lift coefficient decreases and air resistance increases when the aerofoil profile is at 30-degree angle of attack, which is also known as a stall condition. A stall happens in aerodynamics when the angle of attack exceeds a certain point, causing the lift to decrease. The angle at which a stall condition arises called the critical angle of attack. On the lift coefficient versus angle of attack curve, the critical angle of attack is the angle of attack at which the maximum lift coefficient occurs. Furthermore, although the floor separation occurs at short angle of attack, attached flow over the wing continues to dominate. As the angle of attack increases, the split zone on the top of the wing expands, limiting the wing's ability to generate lift. At critical angle of attack, separated flow is dominant, and increasing the angle of attack creates more drag and less lift. Next question. What phenomenon causes the orifice flow to disperse from our knowledge? The effect that happened is the Venturi effect. It is a phenomenon that causes orifice flow to scatter. When a fluid achieves a state of confined flow and its velocity approaches the local speed of sound, the Venturi effect occurs. A further drop in downstream pressure environment will not result in velocity increase unless the fluid is squeezed when a fluid system is choked. A choke fluid system or choke flow is when a flowing fluid at a given pressure and temperature passes through a constriction, such as the throat of convergent divergent nozzle as shown in the figure. Into a lower pressure environment, the fluid velocity increases. As you can see here, the initial velocity increases after it passed through the throat. Next, we will go through questions for our boundary layer experiment. The first question is explain about the boundary layer thickness in the boundary layer of both surfaces. So the height at which the mean velocity reaches 99% of the free stream velocity is sometimes referred to as the boundary layer thickness. The value of a boundary layer thickness is generally minimal for a flat plate with a smooth surface because the viscosity effect is low. In contrast, the viscosity effect is significant for a rough surface. As a result, the thickness of the boundary layer on a rough surface is more effective than on a smooth surface. Frictional forces from the surface cause the fluid flow speed to slow down, causing the thickness to increase. The next question is, what is the distance in the plate before the flow becomes turbulent? What phenomena could be the reason of this change? So for both smooth and rough surface of the flat plate, it is at the distance 70 mm from the x-axis that the flow starts becoming turbulent. Air is flowing over a long flat plate with a specific velocity. The distance from the leading edge of the plate where the flow becomes turbulent and the thickness of the boundary layer at that location are to be determined. When the flow becomes turbulent, the boundary layer thickness starts to increase and the value of its thickness can be determined from the boundary layer thickness relation for the turbulent flow. Next question. This is the last question. What are the differences in terms of result for smooth and rough surface? The velocity results are higher for smooth surface of the flat plate than the rough surface as the resistance of the smooth surface is lower. For rough surface, the point at which the manometer stops to change in height regularly increases as the distance of plate in the y direction increases by 30 mm. The reading for the distance of 30 mm in the y-axis initially stops at the fifth movement of the pitot tube, which is by the interval of 30 mm each, indicating the transverse has entered the boundary layer region. For a smooth surface, the point at which the manometer stops to change is after a few counts later than the rough surface. This is due to the decrease in friction that resists the fluid flow speed. For 30 mm, the manometer stops to change in height at the seventh movement of the pitot tube. That's all from me. Thank you.
Assalamualaikum and hello, my name is Nurhalimah Timothy. My metric number is MA18077. Today I will explain about conclusion and reference. Conclusion. The objectives stated at the early part of the report have been achieved. Finally, it was discovered that variant angle of aerofoil result in different lift and drag force. Aside from that, we may deduct from the experiment 2 that surface roughness impact the boundary layer and the Reynolds number. The rougher of the surface, the wider the boundary layer and the lower of the Reynolds number. Meanwhile, we can conclude from experiment 2 that the boundary layer on a plate is generally affected by several elements such as the speed of the flowing fluid, Reynolds number and plate roughness, and so on. Velocity is proportional to the Reynolds number as proved by the formula Re equal to V times R times L divided by mu. Next is, according to the experiment result, the speed of the flowing fluid is substantially higher for a plate than for a rough surface at a given x location with a uniform stream flowing parallel to the surface. For reference is, first is Shiching H. 1979, Boundary Layer Theory, 7th edition, New York, McGraw-Hill. Second is Yunus Chengel and John M. Chimbala, 2014, Fluid Mechanics Fundamental and Application, 3rd edition in SI Unit. Lastly is Britannica, the editors of Encyclopedia, 2020, Boundary Layer. That's all from me. Thank you.